I'm going to talk about dynamics, the moduli space of curves. These boards are for stronger people. And if you have been to any of the talks about dynamics and modular space of curves, you know that the talk starts with billiards. so instead of that, in order to motivate some of the things that I will talk about in the next two lectures, I'm going to start with some questions, but I'm not going to start with billiards, but we'll get there. So there's no way not talking about billiards. But so I want to talk about three problems. One is just the combinatorial / algebraic problem, which is very elementary, the counting problem, then something about hyperbolic surfaces, and then we talk about billiards. And I want to say how dealing with moduli space of complex curves or hyperbolic surfaces and certain dynamics of certain flows over those will help us deal with these problems. And some parts of the problems are still open, but I just want to talk basically about the connections, and I'll basically mostly talk about the billiard part. So the first problem, the combinatorial one, is related to what is called meanders. And you can draw it. It's a very simple construction of what is called a meander. So basically you have an interval, you have n points on this interval, and imagine you have, or two endpoints, and you have two end circles with the same center. And I have k, which is fixed. And the other side, so now I have two endpoints, and imagine that the length of all these intervals is 1. The other points, if you put, no matter how you put a certain type of circles there, you get closed loops. But what I want to say is that I want to get loops which don't have any self-intersections. And one way of basically producing meanders would be to write 2n, or n, as a1 plus ak. So these ai's of n. Somehow, imagine you do it randomly, or there are different ways of doing it. And then start with maybe you have the first, you wrote the number as 4 plus, I don't know, 6 plus 2. And for each one, do the same thing. Basically, your basic block is 2 ai points. And you are going to put circles with the same center, one side of this line. So basically, once you do it here, you will get a shape like this. Maybe one.
Don't push too hard because you got the attachment down here.
Okay. And maybe 2. And now the question is, when is what you get? Basically, you get a shape, which is, maybe you call it S of A1 to AK. And if it's, you have n points, and then the sum of AIs is equal to n. When is this, say, connected? So when it's connected, it's called a meander. And it's actually, so it's a very simple thing. What you do is that you just follow these being connected. You always get union of, let's see, I don't know if this one, it seems that it's connected. Sometimes it's connected. Sometimes, sometimes they're not connected. And you want to say, well, are they connected? How many connected components do they have? Or what kind of structure you get? And it's, you can just figure it out very easily, I think, for the case where k is equal to. But after that, things get quite complicated. But it's a very elementary combinatorial question. Is there some percentage of time? Is there some like C such that among the first C% of that's what, by this I mean that as n goes to infinity of these shapes are connected, or C0, or what happens as n goes to infinity to all these shapes. So you have all sorts of weird things, and it's basically, if you think about this kind of problems a little bit, it's all, there's a class of problems. You have small piece that you have like finitely many, maybe you can divide something into finitely many pieces. For each piece, an integer will give you a pattern. And then the question is, what happens if you glue these patterns together? What do you get when do you get a connected thing? And you have all sorts of things. Like, or if you like algebraic things, you can easily see that this question is related to starting with the products of elements in the, like permutations. Imagine a and 1 is bigger than all the ni's, and you are looking at the permutations in S and 1. So these are all this is a permutation to the power k1, and all the ki's are less than ni's. 2 ni to the k, this is a product. And now the question is, like, these type of questions are basically you're producing randomly some permutations, and you're asking, what is the cycle decompositions? What can you say about the cycle decomposition of these elements? As like if ni and ki's are basically, in some sense, random, that n is equal to n1, and then what ki is less than or equal to ni, and n goes to infinity. And I have a list of things references that I don't want to forget. And this is an example from a paper by Matthews and Wright. And they show that it's always the cycle decomposition. You can always decompose this as the product of at most r cycles. But OK, so behind all these, these kind of, you can cook up a lot of other combinatorial problems that you want to understand. Basically, you have finitely many, the thing that you get by gluing together finitely many things, and you are asking about the global shape of whatever it is connected or not, and they are very, very, very elementary, even more elementary than billiards are, I suppose. And but behind all these, there's always something about surfaces. That's how it's related to the rest of these talks. And so maybe this is problem number 1. I don't know if the questions are, at least the statements are clear. OK, so number 2 will be something about, so now we move about hyperbolic surfaces. So I'm not going to say actually so much about these at the end, but I hope you will see how they are related to the other things that we talk about moduli space of curves and the dynamics. And the case of hyperbolic surfaces, so you have a hyperbolic surface, you have a surface of genus bigger than or equal to 2, or maybe you have some punctures, and you have a metric of curvature, basically -1, which is complete on your surface. So it can, it's the case of finite volume, but you can, if you want to think about compact ones, that's fine. So you have the upper half plane with the metric dx squared plus dy squared over y squared, and then you have pi1 of your surface S, which acts on it isometrically, so you get a hyperbolic surface. And so the question is about how you can, maybe the genus is too high like this for this talk, it's OK. So the question is how can you, how can you decompose the, OK, there are different ways of, you can draw the isotopy class, homotopy or isotopy classes of curves without self-intersection and decompose your surface into what's called pairs of pans. And then the geometry of each piece is basically determined by the length of the length, which means that the geodesic length of the unique geodesic in that homotopy class. So basically, this is a good way of dealing with hyperbolic surfaces, because the data is in the length of these xi's. And then, so each one, maybe it's x, y, z. The hyperbolic structure inside of this thing is determined just by the lengths of these 3 curves. And all you have to do is to know something about how you glue these, the boundary components. So now we want to see what kind of So if you give me the data of the lengths of the curves and you tell me how to glue them back, I think you can construct very easily a lot of hyperbolic surfaces. But in fact, you can construct all of the marked ones, basically given a combinatorial type of the Pan's decomposition and the length and the way you glue the boundary components. But you can ask the question the other way. That is, given X, what if you list the set of all, so it's alpha, so alpha is a Pan's decomposition on X, or maybe I should say like this, and then you write down the list of lengths of possible Pan's decompositions. There's the 6 of them there. On, okay, so it reads like this. So the set of all the numbers L alpha 1, L alpha 6, such that alpha is a Pan's decomposition on X. So once you fix X, there are different ways of choosing this decomposition. They can get all very long. But the question is, what can we say about the numbers that we get? So what can we say about so there are ways of producing these kind of decompositions. They can get all, they are a simple way of doing it. Like if you have a long curve that intersects all of them, you can just twist everything around that curve once. But there are non-trivial ways of producing Pan's decomposition. So if you have a surface, if you can have a random Pan's decomposition, which would be very long, then you want to say, oh, okay, what can we say about, say, the distributions of L alpha I divided by F alpha j, when basically alpha is a random Pan's decomposition. So the reason for that is that, okay, that's true that given a Pan's decomposition, you can get a surface, but we are basically, if you're interested in understanding hyperbolic surfaces, you want to see what kind of Pan's decomposition do you have on a given hyperbolic surface. You don't want just to glue things, randomly and see like what, you might end up in a completely different surface. So basically, this would be a question about what happens fixing a hyperbolic surface. So at least there is a surface here. This was just combinatorial, but there's a surface here and it's a hyperbolic structure on it. But this surface is basically fixed, and you want to understand these combinatorial patterns you draw on them, and you want to understand like the distributions of lengths of them. For example, you want to say, is it possible that if X is given most Pan's decompositions, basically means, for example, if the sum of the lengths of the curves would go to infinity, is it possible that one of them is actually much larger than the other ones? Or are they roughly the same? Or what is the distribution of these numbers that you get if you normalize them by L, which is the sum of the length? Okay. So this is also something that, even though it's about a given hyperbolic surface, it's pretty difficult to say. You can prove some estimates, but it's very difficult to prove anything about these kind of questions if you fix X. Even though the question is about fix X, the idea is that even though so this point is something in this space, so I'll continue, I'll talk about one more question, but this point is we give you a point in the modular space of curves, which is something completely static, but you want to move things around and get some mileage just from how these things behave as you move around in the modular space of curves. But fixing X, even though you can get bounds, but I don't think it'd be easy to get strong results about these kind of questions. Okay, so one more question, which is most of the talks start, but it's more related to the rest of the lecture. So somehow, I just wanted to mention these problems so you have them in mind and see what, just to motivate the rest of the lectures. And finally, billiard. Oh, this is the third one. Okay, so I guess you all know the problem, but I will just tell you about it again. and different types of questions that you can ask about playing billiards in polygons. And the interesting thing is that the generic question is open. So whatever question you ask about, like you want to play billiard, first of all, you can play billiard, and you don't necessarily have to play billiard in a polygon, but let's assume you do. And OK, there are a lot of things, I mean, some things, or I don't want to, yeah. I should say that there's no way that I can do justice to all the work which has been done in related things. So I'm just going to talk about the things related to what I've been interested in. So maybe I shouldn't say that not much is known about billiards in general case. There are many interesting results. But say you start with a polygon, and you're looking at the basically path of a ball bouncing off the edges of the billiard. So this is your billiard, and going around. So basically, these angles are the same, and then it hits here, and the same, and it goes on and on. I don't know. This is not a good picture, but you just, I don't know what it does. It goes, continues. So you're interested in basically what a ball does going around in the polygon, and it doesn't have to be convex. It can be concave. It can look like this. And if you don't like playing billiards in kind of a boring polygon, you can even play it in something like this, and plus place an edge here. So you can have this thing going, bouncing around, and you don't know what happens. So what are the questions that are very natural? So you want to see what the path of this billiard does. For example, are there closed paths? Infinitely many or not? What can you say about, so the length, it's sitting in C or in R2, that the length really is something well defined, so the Euclidean length of the path. And what can you say about the asymptotics of the number of, say, closed paths of length, say, less than or equal to L, as L goes to infinity? And are there dense orbits? Are the dense orbits equidistributed? So because it's possible that, so there are two things. Like say you want to start at the point and go around. The question being dense or not is if you cover the whole billiard eventually. But it's possible that you cover it eventually, but it's not in a fair way. A fair way would be that if this space has, if this A has bigger area than B, if you take T, go for a long time, like say T, the amount of time your path spends in A should be divided by the amount of time it spends in B should be measure. Measure means just Euclidean area, the area of A divided by area of B. So is it the same? Are the dense orbits, are they equidistributed? Yeah, so these are some questions. But also there's one more question that I want to briefly mention now that I'm sort of bombarding you with problems. Okay, maybe I should mention, first of all, that or it could be light, it's just light starting from this point and then just going in these directions. And I should say that if the ball goes to one of these corners, it just stays there, dies. Just doesn't stop. It goes, there's some hole here and the ball goes in. So all these things like closed loops, and you don't know what direction to continue. It's like all the angles would be the same. And it's closed loop would be something like you all know, like this, I guess, if you have a bad picture. It'll be a high school. Students know that this is there always. You get closed loops in certain triangles like this. The angles are less than pi or 2 pi. So it's kind of so you have closed loops not going through. These are singular points in your billiard. And so, and there's one more question, I mean, two more questions that I want to tell you about. So you want to see the kind of, what would orbits do? And there are some problems called, I mean, and I say these illumination problems. And blocking problems. Okay, so which are trivial for certain type of billiards, at least the first one. Okay, the second one is not, but you basically will have a room which looks like this is your room, and instead of looking at a ball at billiard, it's like light starting from a point, light bulb here. And so the light goes in all the directions. And then, so the walls are made of glass, and then it hits the wall, and then continues and goes on and on forever. And you want to see, if I give you a billiard, and I want to see if you can put the light somewhere so that the whole room is bright. Okay, so for example, for convex billiards, it's trivial, right? So there's the first question. Basically, mostly about the billiards. I mean, it's about billiards which are not convex. Otherwise, of course, you can draw the line joining the 2 points. So it's obvious. So you are interested in billiards. I mean, it doesn't have to be a polygon, but say if it's a polygon, could look really weird. And in fact, there are billiards. So I should make sure that I have all the references. That there are billiards which cannot be illuminated from any point, polygon billiards. And there are billiards which, basically they're not polygon billiards, but wherever you put the light, you get dark rooms, dark areas. Not only that some points are not illuminated, but some pieces of the billiard are not illuminated. And the second problem is like you are sitting, I don't know, they're called security problems, but I don't know. It's like you have a point, you want to put 2 points. So the first point is maybe your child trying to escape, and this is your iPhone. She's trying to reach. And so light starting from this point A, and then going point B. And you want to block point A from reaching B by finitely many points. So assuming that your child goes only straight, it bounces off the edges. But in any case, it's light starting from A. Can I block B by putting finitely many points, which means any path, there are infinitely many, possibly infinitely many paths from A to B. Imagine that your billiard can be illuminated. So can I put finitely many points here so that any path between A and B, you put the dad here and the grandma here, maybe it's like the other people. So any way going this way from A to B, this is not such a good picture, will go through one of these points. And of course, this is, you can see there's a lot of things about this in different contexts. And it's not only about billiards, you can talk about a manifold. So it makes sense in any Riemannian manifolds, or in a very general settings. That is, you have 2 points on a manifold on the surface, and I don't know. And then basically you want to see if it's possible to find finitely many points on the surface such that any geodesic going from A to B will have to go through one of these finitely many points. And there are different results about these problems. And I should say that basically, so these are the list of problems about billiards, which are somehow related to what we will discuss later today and the rest of the lectures. And it's very difficult to say anything about an arbitrary even polygon. So there are examples of billiards which cannot be illuminated, but you can say, like, what is the set of points that cannot be illuminated? I don't know. Generically, what happens? What if the boundaries has certain properties? And I'm sure that, there are a lot of results, but it's really hard to to say anything. For example, this question is open for triangles, for arbitrary triangle billiard. So there are, I mean, and then there are results, maybe I should mention, by Rich Schwartz and Hooper, who say that things about like what happened to the angle. If it's a little bit bigger than pi over 2, you can find it. And it's a difficult problem in the sense that finding the combinatorial patterns of closed orbits is difficult. It's really, combinatorial is a very difficult problem. And the other problems are very difficult too. I mean, nobody knows how to deal with them in many cases. But there is a case which is related to dynamics on modular space of curves, which will give you information about these kind of questions. And that is the case where P is called a rational polygon. So a rational polygon is a polygon whose angles are rational multiples of pi. And all these problems become more somehow approachable. Some of them are still open, but you see there is there's something to do there. You can get a lot of mileage just by looking at the rational polygons. And unfortunately, there are not so many results about stability of things. It's not like you can estimate the polygon by the rational polygons. You can, but it's very hard to relate them if you try to estimate your polygon with rational polygons. So I just want to explain why rational polygons are easier to deal with, and also why they are interesting. Still, they are very interesting. Even though it's like a special case, so why rational polygons? Maybe the main reason is that so if you start from a ball, if you have a billiard ball in P, will have finitely many directions. Or maybe I should say the path, an infinite path of billiard ball in P will have finitely many directions. So if you start from any kind of polygon, to say you're changing the angle, it's just you look at the structure that you have. Like this is vertical and horizontal lines. It makes sense to talk about the angle of a line. And then when you bounce off the edge of the billiard, the angle changes. So basically what you are doing that we will use is that basically what you're doing is that you are, it's as if, I'm sure you have all seen this trick, you know what you're heading. So you are taking the basically reflection of the triangle or your polygon along the edge of your polygon, and instead of looking at the billiard path like this, you're just continuing the straight line. So you can say, okay, so what if I have, so for edges, imagine they have the edges of P, which are E1 to En. So each one will define Ri will be just the reflection along EI. Then you can look at basically if you start the path, you are looking at, so bouncing off of the wall, basically what you are doing is that you're acting by the reflection each time. And the group generated by the reflections, so the interesting thing is for rational polygons is that the group generated by the reflections would be finite in SO2, I guess. So basically, if you start the path, if you're in an arbitrary billiard, it's okay. So you start with some angle, and then the angle changes and changes. So you're hitting the line with an element of SO2, and basically it's a dense. The group is dense in SO2. There's not much you can say. But the rational if you have a rational polygon, then the set of all the directions would be just a finite set. So even though you are going along, continuing, the angles are you have finitely many angles that you can have. So things are a little bit easier. And So how do we maybe I'll keep this question, at least I'll say a little bit about what is known about them. So maybe I'll just say something, I'll mention roughly the result. Let's say for illumination problems, small x, and this one, maybe you can find some references there. But still, even if you are in rational polygons, basically, there are always dense orbits, but there are orbits which are dense and are not equidistributed. But I'll discuss them and you'll see how these statements, there are dense orbits which are not equidistributed. You can say bounds, you can get some bounds about the number of closed orbits of length less than or equal to L, but getting the exact asymptotics is more difficult. It's in families, what do you mean? Oh yeah, if there's, yeah, certainly, yeah. You can have infinitely, yeah, you can have infinitely many. If it can be just, you can have parallel ones, and you're just counting the ones which are parallel are counted as the same thing. I suppose it's like even if you have a billiard which is a rectangle, you have like all these guys are the same, you know. If they are parallel, they are doing the same thing basically. You're counting them as one. Otherwise, you have infinitely many. If you have, in many cases, if you have one, and but the exact asymptotics is something quite difficult, and the illumination problems are also somehow not so easy. I mean, in some cases, one can show that generically, for a generic, whatever means rational polygon, things are, you can illuminate basically every rational polygon, but there are examples of, I mean, there are very easy examples of rational polygons that you cannot illuminate, but in these cases, all the things that are known is like, if you put A, there are finitely many points B that you cannot cover. That's all you can't cover, and you cover the rest of the polygon. So rational polygons. Let's see, what can we do with them? Why are they interesting? So for one thing, so the main trick is unfolding, which says that basically you can, if you start with a polygon, say, that if you have edges which are parallel, so if you start with a square or a rectangle, so the goal is to get into playing it on a surface of sometimes, a compact surface. If you play it in a square, basically, so that's the idea is that you can, instead of playing the billiard, you can glue the parallel edges here and get a torus, flat torus. And if you have more complicated things, maybe you have a triangle. Each time, instead of when you hit one edge, you can basically, it's some simple argument that maybe I'm not going to go through, but basically the idea is that you can do the reflections along the edges and get so maybe if this is, 2 pi over 10, like you have to go 10 times to get a decagon, and then, and then you get a regular polygon, maybe in some cases, and then you are doing the same thing. You are gluing the parallel edges of your polygon, and you get, say, in this case, you get if this is, it's a decagon, then basically you get a surface of genus 2 with, I put 2 singular points, but the reason is that once you do the gluing, something weird happens to the edges, to the vertices of your n-gon. Sometimes the sum of the angles, so almost everywhere you have a structure which is a nice flat structure induced by C, and almost everywhere on your surface you have this flat structure. But of course, the surface of, when you glue these things, you can't have a flat structure on your surface, but then you have the point is that you have finitely many points, which are basically sum of your vertices, possibly, and then, so at these points, the sum of the angles is more than 2 pi. Or maybe if you wanted to play this more interesting L-shaped billiard, you would do this. You take the reflections of this, and then you do this, and these are the reflections. And then you do the gluing the parallel lines. This goes to this goes to this. And what you get is a surface. So instead of playing billiards on L-shaped billiard, what you are doing is that, actually in this case, you have 1, 0, or one singularity. And you see that one of the vertices will end up having total angle 2 pi. But so these guys will not. And then instead of playing billiards here on your L-shaped billiard, basically you are looking at lines starting from, say, some point, straight lines on your surface, and say you are looking at, you are trying to find some closed loops. So, but okay, so maybe I'll say a little bit more about this. So why are rational polygons interesting? Because so they give rise to interesting structures on a surface. Namely, what is called, after using unfolding, they give you a flat structure on a surface of genus G. G is a function of, the edges, there's mi, ni, pi's. If the angles of the polygon are mi, ni, pi, then there's a very simple formula for the genus of what you get by using the unfolding. And so it gives you a flat structure on a surface of genus G of something. Yeah, it's something based on the angles, and so in this case, and basically what happens is that this is always, maybe this is not a bad example. So it looks everywhere flat except for finitely many points, which might come from some of the vertices, and you get a lot of structure. You get basically C, structure coming from C. Not good. A complex structure, which is the same as the complex structure from C. And 2 foliations. So they give rise to and the complex structure will give rise to either, basically, a lot of times it gives you a holomorphic 1 form. So now I call this X, which came from the billiard. That gives you a holomorphic 1 form, or quadratic differential, and then. But that's okay. Holomorphic 1 form. If you are lucky and you always use, at the end of the day, when you always use some orientation preserving. So you have an orientation everywhere on your surface. If you always use orientation preserving maps to glue the parallel edges, basically you get something. You can say that the form which is dz on C will give you rise to a holomorphic 1 form on your surface. And if not, the form dz squared will give you what is called a quadratic differential. The quadratic differential is a form of a quadratic differential dz squared, and in many cases you get f dz, which is a holomorphic one form. So you get, basically, the complex structure is defined almost everywhere except for finitely many points, and by removal of singularities, you can extend it and get a complex, you get really a complex curve by this billiard and the holomorphic one form. So you get a lot of structure. So this here, there is a notion of, first of all, area, just from area from C or holomorphic one form would give you a notion of area or quadratic differential. And also, say in the case of, look at the case of holomorphic one forms, you get two nice foliations from basically vertical and horizontal lines. So the questions that we had about this orbits, you see that, okay, when you look at one orbit in some polygon, maybe these are all, forget about the blocking, these are all rational multiples of pi. When you do this, you go back, and at some point, maybe the curve will have some self-intersection. But when you do this unfolding and you draw it on the corresponding surface, you'd never see a self-intersection in some sense. If you don't go through a singularity, it's something quite interesting. You start at some point and you just continue. And imagine that you have an infinite path of your billiard and it never goes through these singularities. You have basically, there's a notion of straight line, except for this point. And around this point, the notion of these are, the trick is that here you have maybe, these are straight lines, maybe from like vertical lines. At everywhere except for this point, vertical line is a unique direction. And even direction if you're a holomorphic, abelian differential, but basically at least a line field, you have this. So you start here and then you go around, and this line is an infinite line, and it's straight everywhere, and it doesn't have any self-intersection. So maybe you will say, okay, maybe it's something like this. There are infinite lines without self-intersection. You can go and spiral around the simple closed curve, but it's not one of those. It can be dense on the surface. So so already from an orbit of a billiard, you get into some interesting structure on a surface of, say, genus G bigger, or say genus 2 or higher genus. It's kind of the structure of a foliation, and the leaves of the foliation can be dense or not. So for every direction, so maybe this is still about I keep these problems here, or let's see, keep them. So for still the structure is every theta, there is a foliation say f theta, which is all it's the real foliation, the real lines here, for example. The yellow lines will give you a foliation, it's like kind of a foliation of R by parallel lines, which is a measured foliation, meaning that you have a transverse measure defined for the foliation on the surface, measured foliations. And yep. So why? So this one thing is that you get a rich structure really on the surface that you get by gluing parallel edges of polygons, or this kind of unfolding of rational polygons that I didn't quite tell you precisely how to do it, but it's quite elementary and nice. And but the other nice thing is that we can generalize this to the space. They all sit inside a nice space, which is the space of, say, if you are in the orientable case, like abelian or quadratic differentials. And And this space has rich structure. But I'll say what I mean by that. And OK, so let's see where we are. So we have this nice rational polygons. You get a surface. You have some rich structures. But what does it have to do with the problems that we were dealing with? We were interested in closed orbits, dense orbits, equidistributed orbits, basically the paths of orbits. And the nice thing is that in general, I'm sure you've all seen it, maybe some talk when you're in high school, maybe. The nice thing is that you want to do a problem, maybe you can't do it for one polygon, you change the polygon and say that the two problems for two polygons are basically equivalent, and then the second polygon has some other nice properties that you can deal with. But these problems, you can change, you can start from a polygon which looks very nice, and you can, OK, maybe not, and you can deform this polygon in a way and send it, imagine if you have a map from one polygon to another polygon, and imagine that it preserves, so let me just do something very simple, because I can't draw pictures. OK, this is your polygon. So imagine that the map is very nice, and it preserves all the structure that we are interested in. So we are interested in straight lines. So what would be the map that preserves the orbits of elements and send orbits to orbits? Basically, any linear map will change, and so any element that's orientation preserving. And I'm assuming that it also preserves the area just for, I mean, it can be GL2, but I just want to preserve something later. So any kind of linear map in SL2 will preserve all the answer of all the questions that I asked you. So imagine if you have SL2, maybe you acted by the diagonal element. Now, but of course, this could be, you could do it for some other more complicated polygon and make it into something that looks, change. You can squeeze and stretch, and you get the polygon which looks somehow different. But I don't know if okay, I do this. I don't know. But in any case, yeah. But in any case, the answer of these things would be the same for these two polygons, because any closed loop in one, you can just apply phi and go to a closed loop to the other one. If something is dense here, you have a map. This will be dense there. So it doesn't matter. So the reason that we do this and we get these, we glue these things. I mean, and it's also one reason that for rational polygons, things are easier is that, OK, in general, everything is invariant under SL2R. But you have here an action of SL2R. But of course, it changes this, possibly changes your structure. And you can see, like if you look at the complex structure that you get by gluing the parallel edges of a torus, so it's an elliptic curve. It's like when you act by phi, the complex structure is something else, except if you just rotate. If you just rotate, it's like you have a polygon, and instead of putting it straight, you are, moving it, rotating it in the plane. Of course, nothing changes. It's the same thing, but by the way we define things, you get a different surface, which is not very different from but the complex structure is the same. Or you get a different structure on the same surface. So the nice thing is that so there is an SL2R action on the space of rational polygons. I mean, I don't quite mean this space. OK, of rational polygons. And even if you look at each rational polygon, which give you an abelian differential on the space of abelian or quadratic differentials. OK, but unfortunately, these two are not quite the same things. So there are abelian or quadratic differentials that you can get from, so maybe I should define this, that you can get from rational polygons, and there are ones which you cannot, just because of some stupid dimension count. Not every, so what I call, so there's a space, so this is a definition. So each rational polygon, which will give rise to, say an abelian differential. It doesn't really matter for this talk. It's abelian or quadratic. That gives rise to an element. It's an abelian differential, say, on X, which is the surface of, say, genus, fixing the genus. But A1 to AK are basically the multiplicities of zeros or singularities. So you can look at all abelian, okay, you can look at the space of all abelian differentials on a surface of genus 2 or 5, or, so these are nice bundles defined over the moduli space of complex curves of a given genus. But you can also look at the abelian differential, and an abelian differential always defines a flat structure. Now you can look at the zeros of the abelian differential, of course, and look at the multiplicities of the zeros, but also phi dz basically defines, you write it as d of something, and this something here will define a map to C for you locally, apart from the zeros of the abelian differential or quadratic differential, whatever it is. And basically, you can look at the space, which is the space of all abelian differentials, say, with given set of zeros. Like you can say, I have zeros P1 to Pk of type A1 to AK. For example, on a surface of genus 2, if you have an abelian differential, you can have multiplicities. So this is 0. And this picture means that if you draw the real lines at one point, most points, there is only one real line. You have this foliation. But at 2 points, which are the singularities, there are 4 of them, or 2 of them, depending on how you count it, will come out, or 4 of them here, and 4 of them here. And the rest of the place, basically, maybe if you continue one of these edges, it will be dense on your surface. It goes everywhere, and it never have any, it never has any kind of any self-intersection. So it's a weird structure in a way. And so this is the space, and a lot of, some polygons, for example, if you have 1, 0, you can see this. It's easy to see that sum of AIs is equal to 2G minus 2 if you are on a surface of genus G. And so, for example, this polygon, the L-shaped billiard, will give you a surface of genus 2 if you do the reflection, do the unfolding trick. And you will have one singularity, which, we have. And the yellow lines are the images of these lines. Okay, not quite, but almost. This is a, and basically you have the flat structure, and this is a space which has dimension. So this is a very nice space. It has dimension. Maybe I'll just say a few words about it because we want to deal with this space later. It has dimension 2G plus K minus 1 complex. And so if you have a holomorphic one form and it's locally, and it's a space of almost flat structures with finitely many singularities, but it itself has a piecewise linear structure. So what I mean is that imagine if you have in the case of polygons, so polygons, rational polygons will give you elements in this bigger space. But unfortunately, not all the elements here will come from polygons. But in the case of polygons, imagine that if you want to to find out all rational polygons, like the space of all rational polygons, you could basically find a nice coordinate for them based on the lengths of the sides of your polygon, right? And here something similar happens. So there isn't, when you have a holomorphic one form, you have a notion of length. Really, it's just a flat Euclidean length everywhere. You get a metric, which is a flat, comes from the flat length of edges here. And basically, and you get, or if you want to be, if you want to do something fancy, you can say, oh, you intersect, you have two measured foliations, and it's related to the intersections with the transverse measures of the measured foliation. But if not, you can, if I give you an edge, you can give me a complex number, basically by integrating the holomorphic one form. So by using holonomies, you can choose enough lines and integrate one form along these alpha i's. You can use 2g plus k minus one of them and integrate the one form, and you get a coordinate system for the space. So let me just say a few things about this, and then I guess I don't have to. And then next time we will discuss more of the things. Okay, so the space has piecewise linear structure, but it's something that the interesting thing is that the SL2R also acts on the space of given A1 to AK, you get a natural SL2R action on each of these spaces, which are piecewise linear. It's like you have some 2g plus d minus 1 pieces of the Euclidean space, and then you glue these things. You get some space which is not compact, but maybe next time I'll discuss this more. And it has a measure mu which is invariant. So the measure, the piecewise linear structure gives you a canonical nice measure, but the measure which is invariant under the SL2R action. And the interesting thing is that the measure is finite, which is due to, I will discuss, I guess, next time the problems and what is due to whom, Veach and Mazur. And also, the interesting thing is that it's a nice, you can say, oh, what can you say about this action? Because if you start from a point which is a rational polygon, it will give you an element here. If you act by SL2, you move it around, and you get a polygon which is, after you apply SL2, you apply one of these easy things which don't change the answer to the questions that you started with, and you're saying, okay, will you reach to the point that you have nice properties there? So maybe if every point will have the dense orbit, then the behavior of all the rational polygons would be the same. So now we can, maybe I'll discuss this a little bit the beginning of the next lecture, but so it's also known that the SL2R will have the group there, which is generated by it's called the Teichner geodesics, but maybe for now I haven't justified why to call this the diagonal elements and the nilpotent elements, unipotent elements. It's called UT, and this GT and UT, both they act ergodically on basically every connected component of H. So that's a good sign. At least a generic element would go everywhere when you act by SL2. The problem is that rational polygons are not generic. They are lower dimensional things. So even if you can say, so whatever, a lot of statements about generic elements in H, A1, AK, you can't say anything about a rational polygon because it's not a generic element. And so I think maybe I'll finish here. Next time I'll discuss more of the known results here. And basically what I want to talk about in the second and third lecture is statements about the actions of this group, ETE minus T, and the not UT, but the upper triangular matrices on HA1 to AK, and tell you what the problems are. Basically, there's an analogy people refer to all the time between these spaces and either homogeneous spaces or negatively curved manifolds. But this analogy is not so useful in some sense because it's not compact. The non-compact, I mean, the infinity parts of these are quite complicated, and it's not a homogeneous space, so there's not much you can do if you just want to deal with homogeneous spaces. But we want to discuss basically the dynamics of these two and some of the known results and the things that we get by looking at these questions. And I will basically discuss some of my joint work with Alex Eskin and some other collaborators, but maybe I'll discuss it next time. For now, I just this lecture was just problems, and next time maybe discuss some of the methods. And okay, thank you.